All right, last class, we talked about electron configurations and orbital diagrams. We talked about how to read things off the periodic table. And by things, I mean the order that we fill up our orbitals. Does anyone remember where the p block is? It's not the transition metals. I did see some vague gesturing that I think might have been correct. That vague gesturing was, nope, still dead. That vague gesturing was hopefully over to this, we'll get it. Oh, there we go, laser pointer issues. This right area of the periodic table, the right side of our main group. So all of our nonmetals and some of our weird metals and our metalloids. Where's our F block? Yeah, our F block is all the way along the bottom. Our D block? Transition metals. And how about our S block? Alkali and alkaline earth metals, that's right. So whenever we're in the row that corresponds to that block, we're filling out that block. Might as well just go back to the slides. We're filling out that block, and whatever the row number is for our D block, it's the row -1. If we were doing stuff with the F block, then the N that we put, the number that we put in front of our letter would be row -2. So our first one would be 4F, and then we would have 5F. Instead of where they actually show up, which is in the 6th row for our first row. Very clear and straightforward. The last thing that we got to was valence electrons. The valence electrons is kind of the whole point of why we've been talking about this, is to get to talking about valence electrons. So remember in our Bohr model, we had the nucleus in the center, that's represented by this dot, and we had different orbit levels, sort of like the tracks that the electrons could be on. The closer ones are closer to the positive charge, they're more stabilized. The further ones, the farther you go out, are higher energy because they're less stabilized. Our valence electrons are whatever's in our outermost shell. If we just have the one inside shell, just this inside track, then that would be our valence electrons. If we've got extra shells on top of that, then whatever our outermost would be our valence electrons, and everything else would be core electrons because they're all inside the valence shell. And from an electron configuration, we can figure out what the valence electrons are. This isn't the only way that we can do this, and this is arguably a slow way of doing it. We'll learn a faster way soon. But for silicon, if we do an electron configuration, here's our full and complete electron configuration, 1s2, 2s2, 2p6, 3s2, 3p2. Our 1 and 2 numbers, the big numbers in front, these, remember, are our principal quantum number. And 1 and 2 are not our highest number, 3 is our highest number, and so it's just the 3s2 and the 3p2 that are the valence electrons. So we've got 4 valence electrons. Everything else would be core electrons, and if we use our noble gas shortcut, then that represents all of our core electrons. In this case, it's neon, so that has 10. If we were down a row, then it would be argon, which has 18, and krypton, which has 36, and so on and so forth. Let's do an electron configuration for chlorine and figure out the valence electrons and the core electrons. We'll do it the long way. We are working with chlorine. We're going to do it the long way, but the fast long way. First thing we need to do is figure out where are we counting out to, and chlorine is in our 3rd row. 3rd row means we'd be past the 1st row. In the 1st row, we just have two elements that correspond to our S block. So row 1, S block, we're past it. We're past both of those elements. Then we move on to row 2, where we've got lithium and beryllium in our S block. We're definitely past those. This would be row 2, so it's 2s. We're past it, so 2s2. We skip over our transition metals for now. We're on boron up to neon. We're past those. This is row 2, so it's 2. And the block is P. We're past it. The number of things that we counted past is 6. So 2P6. Then we move on to row 3. We're past the S block. So 3S. And then we skip over to aluminum and the rest of our P block. And chlorine is in there. So we have to figure out which spot are we in this block. I should clean this laser pointer, apparently. Anyway, we're in the 5th spot in that row, in that block, so it would be 3S5. Sorry, 3P5. 3S2, 3P5. What's our highest big number? The full-size numbers. The highest number is 3. So these would be our valence electrons. We've got 2 plus 5 equals 7 valence electrons. Sometimes we'll also see that as VE. And for our core electrons, it's everything with a lower number. In this case, that's going to be 2 plus 2 plus 6, 10 core electrons. We could have also used our shortcut to do this electron configuration, in which case we would have written Ne in brackets. Neon has 10 electrons because it has 10 protons, and so that would count for 10 core electrons. And then we would just count out in the row that we're in. So we get 3s2, 3p5, and we would still end up with a count of 7 valence electrons. Fortunately for us, we don't really have to do this most of the time. For a lot of elements, the pattern is the same. So here's just the valence electron configuration parts for our first 3 rows of main group elements. Notice that everything in the 1A or 1 column has 1s1, 2s1, 3s1. What they have in common, they all have 1 valence electron. And when we move over to 2a, our second column, they all have 2. When we skip over our transition metals, now we've added 1 into our P block, our P subshell. And now we've got 2 plus 1 is 3. We add another, we add another, we add another, we add another, we add another. So whatever that A designation column is, when you get over to the P block, the 13 becomes 3A, you just cut off the 1 in front. Whatever this number is with the A designation, that's the number of valence electrons that it has. And that's always the number of valence electrons that it has. So for our main group elements, it's the same for each column every single time. It's the same as the A group number or column number. And it's always going to be that. So if somebody asks you how many valence electrons does arsenic have? AS.
5.
It's got 5 because it's in 5A. What about iodine?
7.
Iodine has 7 because it's in 7A. What about krypton?
8.
Krypton has 8 because it's in 8A. And it's always going to be that way. Questions? So this is why I was saying we've got a faster way. We don't actually have to do the electron configuration. We can learn this shortcut because we know what's going on behind the scenes with the electron configuration. And that's very nice. Here it all is also written out. So the number of valence electrons for any main group element, except for helium, because helium's weird, is equal to the group number of its column for 1A through 8A. This only works for main group elements. It doesn't work for our transition metals, because our transition metals are weird. And then the row number of whatever block we're in is equal to the number of the highest principal shell. Remember that rows go left to right. You would subtract 1 for the D shell. So if we're looking at the first row of the D block, that would be row 4. Subtract 1, it's 3D. What's happening when we are in the transition series, our D block in the middle, our transition metal block represents the filling of core orbitals, core electrons. And for us, that's really all that we need to know. There are a couple of weird exceptions that I think are fun, so I'm going to tell you about them, but I'll try to remember not to put them on the exam. So there are 2 exceptions in the first row of the series, because half-filled and completely filled D subshells are especially stable. We already talked about how to do this. This is how to count. Counting out electron configuration. I don't know why it's here. I don't remember why I put it here. Anyway, while we're here, neon in parentheses, bright green. Neon in parentheses because that's our previous noble gas. We're doing a thing for sulfur. We are past our row 3, S block, so 3S2. We skip across. I spent way too much time making these little cutouts. And then we get into the P block. We're in the 4th spot. It's row 3, so row 3, P block, 3P, 1, 2, 3, 4th spot, 3P4. That would be sulfur. Again, I don't know why I put it here because I talked about it earlier, but it's been this way. And maybe I don't have that fun, cool trick. Nope. Okay, the fun 2 exceptions. Again, I'll try to remember not to put these on an exam. If we are looking at our D block, we're looking at scandium, titanium, vanadium, chromium. Let's look at what that electron configuration would look like for chromium. So chromium's previous noble gas is argon. And then we are in row 4. We are past the S block, so 4S2 because it's too wide. And then we are in the 4th spot in the first row of the D subshell. The 4th spot means that it's raised to the 4, and the 3 in front because it's the row minus 1, so 3D4. The electron configuration doesn't show us why this is stable or why this does weird things. What does show us why this does weird things is if we look at the orbital diagram. So here's our 4s. It's full, so we've got up, down, and then we're going to start our 3D orbital diagram. And our first one we're going to start up, which means that our second one has to be what? Up. If it's up, then it's up, up, up. And we've got 4 in a row. Wouldn't it be awfully nice if we had 5 in a row? Wouldn't that just be so satisfying to see 5 in a row? But where would we get a 5? Where would we get our 5th one from? Theft, burglary. We can steal it. Where can we steal it from? Over here. We can steal this down and flip it up. And so what we would actually see for chromium is that it steals one of these electrons from the 4s to put it in the 3d, because having 5 paired up, pointing up, is really nice and stable. They've got that resonance or symmetry or whatever we would call it. It's just really nice and satisfying, both to look at, but also like on a quantum mechanical scale, it's also satisfying. The other time that we would see this is for copper, which is the second to the last, also in that same row. So copper, same argon, previous noble gas. We would expect that it would be 4s2, 3d9. Again, this is all just for fun. And then our 3d. We've got 9, so we're going to need to fill all of them except for 1. And so the fastest way to do it is just up, down, up, down, up, down, up, down, up. And we're so close. Right, look at that. We just need one more and then we've completed our set. Just one more. This is reminding me of, there's the guy that was looking for the Aldi minis for like forever, and then he finally got them and he was so excited because they sent him the little tomato. Anyway, weird piece of internet lore to insert there. So what happens for this one also is we steal one of these electrons from 4s, we yoink it, yoink. And so it's not actually 4s2, 3d9, it's 4s1, 3d10. Because it's more stable to have it in the 3d, even though that's core electrons. Anyway, so that's just for fun. And I'll put that in parentheses, not parentheses, quotation marks to represent how I'm assuming that we feel about it. Questions about the fun that we're having? All right. I'm going to block this in. This is the review of electron configuration from the periodic table. Using the periodic table. Slide number 58. So if you want to practice coming up with electron configurations, because it'll be on the exam, one of them, if not the next one, this would be the slide to come back to, this 58 and 57, where we've got them actually, it's all shown out to you. So let's use the periodic table and determine the electron configuration for AS. First we need to find AS. And we find it in that area. So go ahead and take a moment, use the periodic table, either one that you have or one not on the board, and figure out the electron configuration for this element. Okay. We used our periodic table, we figured out the electron configuration for AS, or we were confused and we didn't. If we were confused and we didn't, go see Logan in his SI sessions, or watch back the video, or review the slides. This is a skill that you should be able to do. You should be able to come up with an electron configuration, especially for things that are in the main group rows 4 and up. Those should all be relatively easy. I wouldn't give you something that's going to run into F block orbitals because those are big and scary. All right, what are we starting with? Argon. Argon is our previous noble gas. So argon in brackets. What this does for us is it says we're good up until 18. So this covers our first 18 electrons, and then we just need to do everything that's in the row that we're in, which is row what? 4. What's the first block that we run into? S block. So 4s, and we are past it. We're past both of them. We're past potassium and calcium. That's 2. So 4s2. Swap some colors. And then what's next?
3D.
D, and it's 3D. It's really popping off of the board. Not 4, 3, 3D. You can only get 4D in the movies. So 3D, and how many spots are we past in D? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're past all 10 of them. So it would be 3D 10. What's next? We're up to 4, and the block is P. So 4P, and what spot are we in? We're in the third spot. 1, 2, 3. Now, bonus question. How many valence electrons do we have?
5.
Got some guesses for 5? Does anyone have a different guess? We have a guess for 3. Another guess for 5. A guess for 4. It is 5. And it's 5 because we've got the highest n number. The highest number that shows up for our electron configuration here is 4. That's our highest n number. And we've got 2 plus 3 equals 5. The other way that we can figure it out is just based on the column that it's in. So our A designation columns start in the first column, 1, 2A. We skip the D block, 3A, 4A, 5A. So 5A means 5 valence electrons. That's the other way that we could come up with it, completely independent of our electron configurations. One of the things that I see people make a mistake with is they'll count the 10 from the 3D10. And you best believe if I give you arsenic on an exam, one of the options is going to be 15. I will make that an option. It's not the correct option, but it'll be there just to make sure that we know what we're doing. All right, now let's talk about some of the other things that we get from the quantum mechanical model. It turns out the chemical properties of elements are largely determined. A lot of their properties are determined by the number of valence electrons that they contain. This is part of the reason that we have them lined up in columns based on the number of valence electrons that they have. This is also why we were able to make a big blanket statement, not a statement about a big blanket, but a broad statement that our halogens are highly reactive nonmetals. They all want 1 electron. Our alkali metals are highly reactive metals. Our alkaline earth metals are less highly reactive metals, and so on and so forth. And our halogens are non-reactive or inert. So the reason that the element properties vary in the way that they do is because the number of valence electrons is periodic. And our quantum mechanical model gives us a little peek behind the curtain as to why that is. So things with 8 valence electrons, or 2 if you're helium, are particularly low energy. These have fully paired orbital diagrams. Every upspin has its downspin for all of the electrons, all of our subshells, for the rows that we're in. The noble gases are chemically stable. They don't need somebody to give them an electron. They don't need to give away an electron. They're super, super duper stable. This is why we use helium in party balloons and other things that might be around birthday cakes with candles on them, because it won't explode. If you put hydrogen in a balloon, it's also lighter than air, but if you get it close to your birthday cake and it pops and there's a flame there, it's going to make a very big pop because the hydrogen gas is explosive. Google Hindenburg for more on that. This is also true for the rest of our noble gases, which is why you can also do the fun like breathing in the gas trick with argon, but it's more dense than air and so it pitch shifts your voice down. You can probably Google something for that as well. Argon gas breathing, low voice, something like that. And the reason that we're starting with noble gases is because elements with electron configurations close to the noble gases are the most reactive. The closer to noble gases, the more reactive. So if you're just one column off, which is going to be our halogens are one to the left, they're one short, and our alkali metals are one to the right, and then it flips around. They're one to the right, so they've got one extra electron. If they lose that one electron, they unveil, uncover, show off that they actually have noble gas configuration underneath that. And that's going to be really stable. So our alkali metals are the most reactive metals because of that, whatever the rho is our N here, S1 electron configuration. They're just one electron past noble gas. So losing one electron gives them noble gas electron configuration. What's special about noble gas electron configuration? It's very stable. Everything's paired up. We love having everything paired up. And this is why our alkali metals, our group 1A metals, tend to form 1+ cations. They lose that one electron. It's a minus charge. Minus a minus 1, double negative, turns it into a positive 1. This also works for alkaline earth metals. In their reactions, they tend to lose 2 electrons and form 2+ ions. That also gives them noble gas configuration. The reason that they're less stable is because they have 2 electrons to lose. Losing 1 electron is pretty easy. That can just happen randomly. You just bump into somebody, oops, lost an electron. If you have to lose 2 electrons, that takes a little bit more work. Harder to lose 2 electrons than it is to lose 1. If we're going to anthropomorphize our atoms, our elements a little bit. Alternatively, we could think of it as stealing. It's easier to steal 1 electron from somebody than it is to steal 2 electrons from somebody if we're thinking about like maybe their dollar bills. You might be able to steal $1 bill from your friend, but as soon as you start to steal more dollar bills, eventually they're going to notice. Might have personal experience with that. It was a while ago. All right, our halogens, which is our group 7A or group 17, these all have whatever the row number is, S2, whatever the row number is, P5. They are 1 electron short of noble gas configuration. Da, da, da. In their reactions, halogens tend to gain 1 electron. Which is a 1 negative charge. And reach noble gas configuration. So that's why all of our noble gases have a 1 minus charge when they form an ion. It's pretty easy to just pick up 1 electron or steal 1 electron. So our elements that form predictable ions, the silver and zinc don't really work for this, but they do form stable ions, predictable ions. But for all of these, we can see that they're all relative to the noble gases. For our 7A, they need to gain 1 electron. They need to move 1 spot over, gaining 1 electron, to become a noble gas. For our 6A, they need to move 2 spots over. That would be like gaining 2 electrons to get noble gas configuration. For our 5A, they need to move 3 spots over to the right, gaining 3 electrons, gaining noble gas configuration, which is especially stable. So the goal is nobility. The goal, in terms of gaining, losing electrons, is to become a noble gas, even if you're not really a noble gas. For our metals, they all lose 1 and then it wraps around. So for lithium, it wraps around to helium. For sodium, it wraps around to argon. For losing 1 electron, for magnesium, calcium, strontium, etc., we're losing 2 to become like noble gases. Aluminum's losing 3. So that's where the predictable ions comes from for our main group elements. We also have some trends that we can talk about with the periodic table. We've got, I think it's 3. It is 3. We have 3. There's more than just 3, but we're going to talk about 3. The first one, trend number 1. And for these trends, 2 of them are the same pattern, 1's a different pattern. You can choose to learn the underlying reason why, which I think is powerful and cool, or you can just memorize it. Nice. So for atomic size, what we're talking about here is the distance between the outermost electrons. What do we call those? Valence electrons. So it's the distance between our valence electrons and the nucleus. What's in the nucleus? Protons and neutrons. And I'm going to run out of space, so I'm writing n to the 0. So our nucleus, drawing out a Bohr model because it's the easiest to think about. The distance between whatever our valence electrons are, let's say that we've got 2, and our nucleus. It's this distance. Atomic size. It's our radius. I think it's the radius. Could be the diameter. It doesn't really matter. The trend is going to be the same either way. So across the period, so moving left to right, your left to your right, across the periodic table, atomic size goes down. But Mr. K, we're adding electrons. Why is it getting smaller? Thank you, student. That's a great question. The reason that it gets smaller as you go across a period is that the number of protons in the nucleus is increasing. So there's protons in the nucleus. Those have what charge? Positive charge. And the electrons on the outside have what charge? Negative charge. So if we have more positive charge on the inside, is that going to pull our electrons in more or are they going to be farther away? Negative charge, positive charge. Opposites attract. It's going to pull them in slightly. So that's the reason that it decreases as we move left to right. We're adding charge, more protons on the inside. That's going to pull our valence electrons in. So increased charge, positive charge in the nucleus pulls the valence electrons in. And so we get an unexpected result, that it goes from large on the left side to small on the right side. The other direction that we can travel is up and down. When we move down a column or a group in the periodic table, atomic size increases. We are adding another layer of electrons on. If we're thinking about our Bohr model, we're adding another orbit on, so of course it's going to get bigger. So we're adding an extra layer of electrons as we move down. And since we're adding another layer, those outside layers are going to naturally be further apart, further from the nucleus in the center. That's not the right way to draw these. This way. Oop. Something like that. Looks like a snowman. Questions about atomic size? So left to right, what happens? It decreases. So on the left side, big stuff. The right side, small stuff. Top to bottom, it increases. So for our atomic size increases as we move to the left and also as we move down. So just based on this trend, which of our elements is going to be the biggest, the largest? We would expect that it would be francium, because it increases right to left, it increases top to bottom, so we would expect FR to be the biggest. For real. I don't think that's actually quite true. It might be, but doesn't matter. We want to choose the larger atom in each of these pairs. We've got comparisons. PB and PO. I will draw in their relative ordering to save us some time. So on the periodic table, you would find them next to each other. They're in the same row. PB is on the left, PO is on the right. Which one's going to be bigger? PB is going to be bigger. Then we've got RB or Na. It's going to be RB because it's further down. So down and to the left is larger. So those are easy. And then we've got SN or BI. We've got SN, Bi, tin and bismuth. Left to right, which one's bigger? So SN is bigger. Left, right. Which one's bigger, top, bottom? Or up, down? Bi, bigger, up, down. Which effect do we think is larger? Adding on a whole layer or a little bit of electron shrinkage? Adding on the layer is probably bigger. So bismuth, almost definitely bigger. What about F or SE? It is going to be SE. It's bigger in both directions. It's further to the left by one column, and it's down 2 rows, so it's definitely bigger. Questions about figuring out those sizes? I like to ask at least one question on atomic trends on the exam. It might even be one on each of the questions, or on each of the trends, but I don't remember. You should know them, though. Okay, so in review, this is our bigger directions. Bigger if you're further to the left, bigger if you're further down. We also have ionization energy, trend, the second, trend junior, if you will. Ionization energy is the energy required to remove an electron. That's kind of the most important part, but it's also supposed to be in the gaseous state. So how much energy does it take to pluck an electron off when you have it in the gaseous state? Ionization energy increases as you move to the right across a period. And this one is nice if we think about just the overall, the far left side versus the far right side. We're taking off one electron. On the periodic table, if we're doing like our counting stuff, that would be moving one spot to the left. So for lithium, if we take off 1 electron, then it would become like helium. Does it want to do that? Does it want to become a noble gas? Would you like to become a billionaire? Would you like to have $1 million? This is their equivalent. So lithium, losing 1 electron, becomes like helium. It's a noble gas now. It's very stable. It's got generational wealth. So it wants to do that. That's a good thing for lithium. Lithium's happy to do that. It's not too difficult. Fluorine, on the other hand, if we were removing an electron, which direction are we going? We'd be moving one spot to the left. Which way does it want to go? Does it want to become oxygen or does it want to become neon? Wants to be like neon because neon's a what? Noble gas. So gaining 1 electron would be so sick for fluorine. We are taking 1 electron away, which is going the opposite direction. This is like you're saving up for a thing that you've really wanted for a long time and you're like, I just need $50 more, and then you get a parking citation and now you're out $30 or whatever it is, $200. I don't know what it costs because I've never gotten one. But that's sort of what it's like. So removing from a 7A is the wrong direction. Seven A wants to gain electrons. And for our 1A, this gives noble gas configuration. which is very nice, very stable, 2 thumbs up, would recommend. If we remember way back, our metals on the left side of the periodic table like to lose electrons. Our nonmetals like to gain electrons. If our metals like to lose electrons, they're more likely to lose electrons. They're okay with it. Our nonmetals on the right side, not okay with it, unhappy. So ionization energy is how much energy does it take? It takes more energy to take it off from a 7A element. So on the right side, big ionization energy. The left side, small ionization energy. It also decreases as you move down a column. It's easier to remove an electron when it's further away from the nucleus. Because it's a valence electron. So if we're thinking of not for scale Niels Bohr models, if we've got hydrogen and it's just got 1 electron and it's really close to the nucleus because it's sitting on this first track, that's going to have a relatively strong attraction, versus if we have 1 electron on this third track, it's a couple of tracks removed from the nucleus now, that's going to be a lot easier to pluck off or to pull off. So for ionization energy, our trend is that it increases up and to the right. Those are our directions of increase, which is the opposite of atomic size. So if you want to know the why, we talked about the why. If you just want to memorize it, there you go. And now let's do some examples. We want to choose the element with the higher ionization energy in each pair. We've got Mg and Sir. Which one's going to have the higher ionization energy? Mg is going to have the higher ionization energy. It's smaller. The electrons are held a little bit more closely. It doesn't have that many electrons. Please don't take my electrons sort of vibes. So magnesium, higher ionization energy. We also have In or Te, and those are related like this. That's all right. Which one is higher ionization energy? Te is higher ionization energy. It doesn't want to lose an electron. It's so close to becoming a noble gas. It just needs to gain 2 electrons. Taking 1 away would make it 3 away. It doesn't want to be 3 away. It wants to be 2 or fewer. And then we've got C and also P, and those are related to each other like this. Carbon and phosphorus. So we've got both directions in play. Which one is higher energy left-right? P is higher energy left-right. Higher ionization energy for the left-right. What about the up-down? Carbon is the higher ionization energy up, down. Any guesses on which one wins? I'd probably guess C, but it would be a guess. So we're going to write C, maybe. It's a thing that you can look up, but just because they're closer, I think that's going to have a bigger effect than being moved over one spot. I don't know if that's true. Do you think that I would give you this on an exam if I'm telling you that I don't know what it is off the top of my head? No, probably not. So some reassurance, if you have multiple trends, if you've got two trends happening at the same time, up and down and left and right, they're always going to be additive if they show up on an exam. Or it'll just be left, right, or up, down. All right, what about F or S? F or S, it's F. It increases up, it increases to the right. And fluorine is further up and further to the right. So it's bigger on both counts. And then we've got metallic character. Metals tend to lose electrons in their chemical reactions. We just talked about this. And nonmetals tend to gain electrons. So metallic character, how much of a metal are you? Are you a super duper metal? Are you an exemplar of metals? Or are you not very metallic at all? Where do our metals live on the periodic table? Left side, right side? Left side. So left, right, which side do we think is more metallic? Left or right? Left, because that's where the metals are. The right side's where the nonmetals are. So it's going to be increasing to the left. Metallic character is how easy it is to lose electrons. It's basically just the opposite of ionization energy. Metallic character decreases as you move to the right or increases as you move to the left, and it also increases as you move down a column in the periodic table. So this is the same as atomic size in terms of the trend, the way that the trend works. So it increases to the left, that's where our metals are. It also increases top to bottom. The electrons are further away, they're easier to pull off. Choose the more metallic element from each pair, Sn or Te. It's going to be Sn, the metals on the left side. Tin is further to the left, so it's more metallic. We've also got Si or Sn. It is Sn. It's further down. It's also a metal. Sn is tin. Silicon, famously a metalloid, or a semi-metal used in semiconductors. Then we've got Br or Te. Te, because it's further to the left, and it's also further down. So it wins on both counts. Then we got Se or I. The shrugging emoji. But bigger left, right. Which one wins left, right? Se is more metal, left, right. And iodine is more metal, metallic, up, down. Wouldn't show up on an exam. Questions? So those are our three trends. Very fun, very fun. So we talked about atomic size, the distance from the nucleus in the center to the outermost valence shell. What direction did atomic size increase, left or right? Just to the left. And up or down? Down. Second up, we had ionization energy. What's ionization energy? What are we measuring? The energy required to yoink an electron, remove an electron. And so that's going to increase which directions? To the right and up. So that's opposite of atomic size. What about metallic character? Metallic character is the same as atomic size. Just write a short down arrow. So if you just want to memorize it, here you go. That's what you memorize. It's two things with two arrows each. Shouldn't be too difficult, hopefully, 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 hopefully. All right, building. We've learned some things. We're adding another layer to our cake. If you don't have the previous layers of the cake, what happens if you just throw a piece of cake in the air? It falls. It's just going to fall and break. And then you're sad because you don't get your cake. So we have to build up our base. This whole chapter, we're building, 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 building. We're like halfway through the chapter. So we have to have everything that we learned before in the previous chapters, previous parts of the chapter, adding on top of each other to get further up. What we really need to know for bonding theories is the valence electrons. We are going to be learning how to represent valence electrons as dots. It's not that hard, but the rest of the stuff that we do with it can be confusing. So we've got bonding theories. Bonding theories predict how atoms bond together, how they connect together, link up to form molecules. These will predict what combination of atoms will form compounds and what do not form compounds. They can also predict the formula of the compounds. They can also explain the shape of the molecule. And the shape of the molecule can determine some of the physical and chemical properties. That's sort of where we're working towards, and we'll get there, but probably next week, Thursday, probably. We are going to be using Lewis theory because it's simple. So Lewis theory, our valence electrons are dots. One valence electron, one dot, not the candy, not the ice cream. And they're surrounding the symbol of the element. So for example, carbon. Carbon has dots. How many valence electrons does carbon have? It has 4. Why? It's in the 4th column. So if we're counting over, starting from the left, right, we've got in its row, lithium, beryllium, skip over the transition metals, boron, carbon. Column, 14 group, 4A group, 4 valence electrons. We could also do an electron configuration if we really wanted to. I don't want to. It gets 4 dots, one in each of the cardinal directions, north, south, east, and west. The result are Lewis structure or dot structure or Lewis dot structure. The electron configuration for oxygen. Oxygen is in the same row. It's just past helium. We'll save ourselves the tiniest bit of time, maybe, writing helium in brackets. Then we are in the second row, row 2. So n equals 2. We are in the S block first. We pass the S block. with oxygen? Or are we in the S block? Is oxygen in the S block? No, it's further. So we're going to fill that in. 2s2. We've passed 1, 2, lithium, beryllium. Then we move over to the P block because that's the thing that comes next. So 2p. And what spot are we in? We are in the 1, 2, 3, 4th spot is oxygen. So 2p4. How many valence electrons? We have 6 valence electrons. We could have also just looked at the periodic table. It's in 6a. It's got 6 valence electrons. So our Lewis structure for oxygen. Oxygen is our symbol. We've got 6 electrons we have to put in there. We've got 4 directions. I'm going to fill them in singly first, and then we'll double them up. It doesn't matter where you put the doubles or the singles. Just as long as you've got 2 doubles, 2 singles, for a total of 6 electrons. They could be doubles on the top and the left, top and the right, or so on and so forth. Wherever you want to put them is fine. So each of our dots, each dot, each of these, 1 valence electron. We put a maximum of 2 per side. It's not really critical where we put them in. You can fill them in singly first if you're just going to count them out. Just pick a direction to start going, pick a spot to start going. 1, 2, 3, 4, however you want to do it. 1, 2, 3, 4, 5, 6. Or if you know where there's how many doubles there are going to be, you can just start with double. Just don't do it wrong. So right, you wouldn't do this. You wouldn't put 3 doubles and then leave a side blank. That's the thing that we don't want to do. Don't start with doubles, start with singles, and then pair them up after that. Atoms with 8 valence electrons are particularly stable. Why? Noble gases. Also, they're full. I'm especially stable when I'm full. If I've had a good meal in me. If I'm not full, if I'm hungry, if I'm hangry, things can get weird. So this is, again, going back to the noble gas configuration. And I'm going to write electron configuration so that it's clear what we're talking about. Full valence, which just means outside shell. So our outermost layer is full. Our defenses are shored up. Eight dots is called an octet. If you're walking around, you see 4 men singing. What would you call those 4 men singing? What would you call their group? A quartet. Quart for 4, oct for 8, octet. What if it's just a man and a woman singing? Duet. 2 electrons, duet. Just in case we're not doing those brain connections by ourselves, I think those brain connections are helpful. Octet, 8 group. The et part is just the group. All right. We've looked at it very briefly. I'm going to give you a shot. Write the Lewis structures, the Lewis dot structures, the dot structures for the first 10 elements. If you have the slides, you can just add the dots. All right, that was a little bit of time. Hopefully at least enough to get started. Hydrogen. How many valence electrons does it have? 1. Helium, how many valence electrons does it have? 2. I'm going to write them paired up because that's a full shell. You could, I guess, also write it with 1 on each side. That's what I would have expected you to do because you're supposed to fill them in singly first. Lithium, how many electrons do we have? Yeah, we're restarting with 1 because it's got 1 valence electron. It has 3 electrons, but only 1 of them is valence. It's the first entry in the second row. So this was the trick for this exercise. Beryllium has how many? 2 valence electrons. How many does boron have? 3. We're doing a counting exercise. How many does carbon have? 4. Are we tired of counting yet? How many does nitrogen have? 5. Oxygen, 6. Fluorine, 7. Neon, 8. Unhappy with that dot. Lewis structures. Do we have questions about any of those? I'm hopeful that if we aren't set up, because this is sort of a setup, that if we aren't set up with, hey, let's do them all in order, and then it's not actually exactly, I'm hopeful that this is something that all of us can do pretty much right off the rip, right off the get-go, right off the bat. Helium notably is stable with a duet 2 electrons. So it's chill. It's happy with 2. We are going to use those dots, hopefully for good and not for evil. And the way that we're going to use those is to represent bonding. So in Lewis theory, a chemical bond, the thing that connects atoms together, involves the sharing or transfer of electrons. You can do either. We're going to mostly focus on sharing, but we will talk about transfer. And the goal is stable electron configurations. What's the stable electron configuration? Eight electrons, noble gas configuration. Noble gas electron configuration. That's the goal for bonding. The 2 types of bonds that we have are ionic bonds. Ionic bonds involve a transfer of electrons. These are notably seen in ionic compounds. Things that have a metal and a nonmetal, or things that have a cation and an anion. So ionic bonds, we are transferring the electrons. The electrons are, we're thinking of them at least as being given from one atom to another atom. In covalent bonds, the electrons are shared. What does the co in covalent mean? Together, like cooperative, working together. So that co means together, it means they're shared. And this is in molecular compounds. Molecular compounds have covalent bonds. Molecular compounds being things with nonmetals only. So just in that upper right part of the periodic table, that's where our nonmetals live. Our octet rule is that when we are doing the chemical bonding, the transfer or sharing of electrons is to obtain outer shells, valence shells, with 8 electrons. Either by giving them away to strip off the outer shell, or accepting them to build up your outer shell, or by sharing them with friends, and they count for both of the shells. We'll talk about that all on Thursday. Questions? Dying questions? Urgent questions? Cool.